Starts here. There we go. Recording has started. So the ISA Twin Cities chapter is pleased to announce Tech Talk session with Pleora Technologies. Pleora serves more than 1,500 customers in industrial automation, medical imaging, security, and defense. On this session, Ed Goffin and Dwayne Lachance will discuss trends in machine vision as the technology expands into new markets, including security, medical, and embedded, with a deeper view into how vision and AI are moving into manufacturing applications. A little bit of a bio on each of these folks. Ed Goffin is the VP product marketing, Vice President of Product Marketing for Pleora Technologies, leading supplier for AI solutions and video connectivity products, quality inspection, and factory automation applications. Over his 25-year career, he's been widely published and is featured speaker on topics ranging from packet switching and network timing to real-time video solutions for situational awareness in medical, factory automation, and security applications. And then Dwayne Lachance is product manager for manufacturing solutions at Pleora Technologies. Again, leader supplier of manufacturing video connectivity for quality inspection and factory automation. Dwayne has spent nearly 20 years in IIoT and manufacturing analytics space, assisting some of the world's leading manufacturers with their data collection and continuous improvement efforts. So the ISA Twin Cities chapter welcomes Pleora to this Tech Talk. And from there, I'll turn it over to you guys. Thank you.
All right, thanks. You can see my slide all right? It's
great.
Perfect. All right. I have, I'm often in the dark, but I've never presented in the dark. So we'll see how this goes. But thanks for the introduction. Now I don't have to cover really slide one about who we are, other than I guess you see Dwayne's face on the screen and me in the dark. Usually I'm better lit than I am right now. So yeah, we're going to talk a little bit about some of the trends in machine vision. Sort of specifically, I'm going to look at the area of embedded and usability, because it's areas that are a little bit different for Pleora. You know, over our 24 years, embedded is definitely a new technology that's come up in the last couple of years, and then usability is something that came up for us a few years ago on a military project, and then it all sorts of fits together around AI and vision for manufacturing. And we'll go over a little bit of why AI and vision has a role in manufacturing. Dwayne can demonstrate some of the technologies. We usually put Dwayne on the spot and make him run a demo or at least a video in some of these sessions. So he gets a little bit of stress there too. And then we can answer questions. I don't have a ton of slides. Well, I say that. I have a fair number of slides, but we'll go through it. You can ask questions during, you could save your questions to the end. I'm good either way. So just really quickly on who is Pleora. So like EJ said in the introduction, we've been around since 2000. We're headquartered here in Ottawa, Canada. We have about 75 employees around the world, including online the illustrious Jason Frank in Minnesota, who covers the US for the entire company. We're really founded around standardization of machine vision connectivity, so connecting cameras or imaging sources to processing. And along the way, played a lead role in developing a lot of the standards that then helped really drive machine vision into the automation market and now into new markets, specifically the GigE vision standard and the USB 3 vision standard, where we played a role in developing those standards and continue to play a role a few decades later in, you know, stewarding those standards and guiding them as they evolve and change. When it comes to markets, you know, we're designed into industrial automation types of applications, security and defense, which I'm going to touch a little bit in the slide around a couple of applications there. And then medical imaging. So I like to say, if you've ever had an X-ray, whether that's medical or dental, you've inadvertently used one of our products. We're designed into most medical X-ray applications as the interface that provides the X-ray image and data back to processing. Over the last couple of years, you know, we took some of the some feedback from customers, some feedback from just the general market, and started moving more into manufacturing solutions with a software suite that I'll touch on a little bit that's around designing AI and machine vision applications, and then a full turnkey solution that Dwayne will talk about a little bit more that's really intended on bringing AI decision support more to manual manufacturing processes. So as a company, we sort of serve these what look like fairly unique end markets in terms of machine vision connectivity, manufacturing solutions, and then rugged networking is what I'll call the military space. But there are a lot of parallels, and you'll see as I go through this set of slides between the markets, and we've been able to learn from the machine vision space around where the market is going in terms of embedded. That's helped guide some of the strategy around what we're doing for manufacturing. On the rugged networking side, we learned a real lot about usability and requirements for humans in interacting with technology, which had not been something that we'd typically been into, and again, been able to bring some of that learning back into the manufacturing market. Plus, just when it comes to computing options across all three of these markets, or networking, or like I said, usability. So for trends in machine vision, when Jason asked if we could, if Pleora could do a session here, and I sort of put some thought into it, and I mean, there's tons going on in machine vision, and I could talk for hours on all sorts of different areas that the vision technology is moving into, or challenges that we're facing around supply chain issues. We're hot out of COVID, right? And changing world demographics in terms of where is manufacturing moving, and is it going from China into other countries and that sort of thing. But I decided to sort of narrow it down and try to look at really where embedded technology is starting to appear in machine vision. So just as a bit of a backgrounder, really for, since even predating Pleora, I mean, a machine vision system typically looked something like this. At one point, it was proprietary connections between a camera to processing, in 2000 type time frame with the evolution of standards like GigaVision. These proprietary connectivity solutions became more of a standards-based approach, where you could then take advantage of networking, multicasting, and cabling benefits of Ethernet. Mostly, networking, obviously multicasting, gathering images from a number of different camera sources and networking them over a switch. Cabling was actually one of the bigger things that drove the evolution of GigaVision. All of a sudden, you went from sort of a maximum of 10 feet of cabling to 100 feet of cabling. And cabling became more flexible. So you could start to move processing out of that manufacturing environment and start to centralize it. So for 2 decades, basically, machine vision looked something like that. On the machine vision camera side, there's, with new sensor data and technologies, always increasing throughputs and increasing frame rate. So what a camera could do a few years ago has changed dramatically today. A lot of times these were going to a centralized processing, so you'd be running multiple cameras on a manufacturing line, but all of your processing was being done in a centralized PC. And for the end user, you still required a high degree of expertise, both in terms of developing your applications, so a machine vision algorithm, was coding, and even just implementing and deploying and managing cameras. There's a certain amount of complexity to a machine vision camera. And as an industry, we sort of ran like this for decades with systems that look like this. Over really the last couple of years, that's really started to change. And it's sort of what I've called these disruptive data sources to the right. All of a sudden you have the emergence of lower cost single board computing platforms that can support vision and sensing capabilities. You have embedded platforms, companies, NVIDIA making huge strides into machine vision. integrating processing with applications and especially focusing on AI over the last couple of years. And then you have a lot of just, types of applications that at one time were in a camera, all of a sudden we have access to as a consumer in our phone. It gets amazing what types of applications you can now run on your phone that once was the domain of a machine vision camera. I always say, my doorbell blows me away. What it can do in terms of, it costs $70. It has sensing, networking between, a camera and the doorbell. I can talk to people in real time. If I'm curious, I can zoom down the street and look and see what my neighbors are all doing, all from an $80 camera, right? Whereas, even a few years ago, that was a $1,000 machine vision camera. So that's really putting a lot of pressure on traditional suppliers. Even a supplier like Pleora, right? We had traditionally been supplying hardware and then software that was going into machine vision cameras. Now all of a sudden we have to start thinking about more of a software solution for embedded devices. And then understanding how these embedded devices and applications fit into a network. When it comes to embedded vision and sensing devices, there's a lot of advantages, primarily cost, right? A few $1,000 camera is all of a sudden now $100 Raspberry Pi board. It's easier to access components for these products if you're designing a vision or sensing application. There's advantages around power. There's advantages around footprint. They're very easy to customize for an end user, whereas in the past, programming a machine vision camera or application could be complex. All of a sudden, that's at the hands of an end user through fairly common SDKs. The big change is really around flexibility. So all of a sudden, where you were sort of locked down to processing at the end of the line, it's much easier for someone to put processing and image gathering and data gathering at various points in a different application. A prime example would be robotics, where a few years ago, it was a camera at the end of a robot and a processor attached somewhere at the end. And now all of a sudden you can start to integrate different imaging sources into that robot. You can start doing processing at those points, feed process data onto the next point so that that robot can make a decision based on vision process data. IoT or IIoT types of applications where you've got a combination of imaging and data sensors in applications. In a lot of, I guess my lights have gone off here. Not quite for that type of application, but I mean, similar applications where I've seen, in large scale facilities where they're using data from an imaging or a sensor to decide, when does lights turn on and off? What do I do with power in a building? What do I do with AC? What do I do with heating? And then, of course, ADAS or assisted driving, a huge market for embedded processing, right? When you think of in your own vehicle, the number of sensors that all of a sudden you have in your car, and then more and more of those sensors making decisions for you, right? For keeping you in the lane, making sure your hands are on the steering wheel, all of those sorts of things. Well, we're making a lot of strides in embedded, and when it comes to vision and imaging, there are some real tricky challenges that still stand out in my mind. One is, going back to what helped drive the evolution of machine vision was that GigE vision standard. And again, here it's really easy to design these devices. Networking these devices can be a little bit of a challenge, right? Passing off information from device to device. And then more importantly, integrating with, in the case of manufacturing, the factory floor systems that you have in place, whether that's PLC connectivity or ERP, MES types of connectivity. And then the challenge is also always around processing latency, especially for real-time applications. So there are some unique capabilities that a designer still requires to make sure that these devices can work in a real-time type of application. I mean, obviously in the automotive space, those guys are solving it, right? My lane assist tells me right away as soon as I start to hit that yellow line. In other applications, there can be a little bit of latency around that decision. And then on the other side, there's also this new range of smart devices, and that includes, cameras. What I've shown here is a company, LabForge, actually Jason's customer. They're based out of Windsor. They do a sensor-based smart camera, and it costs a couple of $100. And built into that camera are a couple of applications around object detection and edge detection. Really simple to use. Even I always say even I can get it set up in a matter of minutes, and you can start doing sorting based on it. It can sort out, tomatoes based on color, all sorts of things like that, all from a single sensor camera. And then below that, I've just shown it's an NVIDIA box. It happens to be one that we use in a couple of different applications, but like a hybrid AI type of edge device that is an easy way to add AI intelligence to an installed vision system or deploy AI on a factory floor. The product that Dwayne will take us through uses this as its processing core. With these devices, one of the key focuses, and I think LabForge are working to solve this as an example, is really around making it easy to develop and train AI models, giving you templates and tools so that an end user can do this. We're following that same path when it comes to different software development tools, where we're trying to give an end user the templates and the tools so that they can start to develop their own machine vision and AI algorithms. And then a real focus on how do I integrate these devices into a factory floor to receive, process, transmit data, trigger an action. If in the case of the LabForge camera, it's sorting out tomatoes and there's poorly colored tomatoes on a line, triggering a PLC to then remove that product and integrating that directly into the device. From an end user perspective, when it comes to all these smart devices, whether it's a camera or an embedded device, the growing expectation is that these devices have to be easy to use. Where once vision was the domain of a machine vision expert, now it's becoming the domain of a quality manager on a manufacturing line. Most of the customers that in Dwayne's business that he deals with are not machine vision experts. They're quality managers who want to own this process. So for that to be a reality, the process has to be easy and simple. It needs support for multiple applications, open source support, the ability to then customize some of these models, and that's around traditional machine vision tools like measurement and edge detection to more complex AI tools like object detection or character recognition. And then they need to connect with what you have on the factory floor simply and easily without a lot of integration work required. Those are the user demands. In reality, where we are right now, not quite there. It still can be a little bit difficult to train cameras in times. You still need a level of expertise. In our own nomenclature, we're going down this no code path of software development, and I think we've more tuned it to low code. You still need a little bit of coding expertise to develop programs to run on some of these applications. So then what do these look like now in a vision application? So thinking back to my first slide of what did this system look like? It's not considerably different, but there's a couple of nuances. So then on the right side, I'll start on the right. So here I have a machine vision camera. Let's say this is a retrofit application. It's a traditional machine vision camera running a machine vision application. As a system integrator or a system designer or a process engineer in a facility, I can now start to use embedded processing to basically make that traditional machine vision camera a dumb camera, make it a smart camera by adding some embedded processing. So here I show the camera, it's gathering its images and data that it needs for the machine vision part of this application, passing it off to edge processing there in the middle of that black box. That black box is now taking that machine vision video and image data and applying an AI skill to it. That could be an object detection. The typical type of application here is the machine vision algorithm does a really good job, other than when it comes to false positives. So machine vision can struggle with some of those. Machine vision makes really good binary decisions, but not as good when it comes to subjective decisions. Or when things change in the environment, it will signal that that product's no good. And then the line stops, and then workers have to start visually inspecting products. A lot of the time it's false positive. The product's actually good, but it's within that tolerance that machine vision struggles with. So with the embedded processing idea, you can start to add some of that subjective decision making that AI is good at. Within the embedded processing, then you also start to integrate your PLC connectivity there. That could be triggering a sorter or a robot or a blower to knock a product off a line. And then you also have connectivity to ERP MES systems. I think Dwayne will probably touch on some of that connectivity in the processing that he runs in his application. The embedded processing box adds this AI skill and then feeds the now AI enhanced video back to processing, where machine vision takes over again. For all purposes, the machine vision processing just sees the video as it had before. It doesn't really realize this AI skill has been added on top of it to help supplement the decision. On the left side, this is also what changes a little bit, is all of a sudden there's a focus on the end user in these types of applications. Whereas before, it would be a machine vision expert designing these algorithms. Now you can start to put some tools into the hands of a quality manager so that they can start to build their own AI or vision applications, train them, and deploy on the model. This is especially helpful in applications, sort of lower run types of applications where there's a lot of switchover on a product line, scalable applications where a quality manager wants to develop an application and then roll it over across multiple lines or multiple facilities. There's a real push to then not have system integrators in consistently to be doing this work. They would like to own it on their own, in our experience. And then that also makes a little bit of a change on the very top there, in that within our own solution, we all of a sudden now have to worry about user interfaces for how do you configure and manage these applications. Again, it hadn't been something that we'd really thought about a couple of years ago. We were really that connection between the camera and processing. Very similarly in the embedded world, again, the same thing, and I'll start on the left.
Ed, do you got a chance for a question?
Yeah, sure.
And prior slide, Ed.
Yep.
This slide.
If I consider that some of the markets that we have in the Twin Cities area in Minnesota, we have a lot of agriculture, right? A lot of food processing. We have some, some pharmaceutical manufacturing in both, pill form as well as liquids. And so what would change in this? What segments would change if you were doing a multispectral machine vision, or say a quality control application in food processing? If you're looking for what should I say, diseased fruit, and you're seeing a different spectrum of light being reflected, whether it's under UV or if it's some other infrared or something, what would change here? Would it be the camera, the lens, the processing system, the AI?
Yeah, that's a good question. So it would really be the camera if you're looking at hyperspectral applications. So we've gotten into a few of those types of applications with a camera partner that we work with on the hyperspectral side. There it's been more around food and looking for their company specializes in two things. One is looking for food quality for grading. So different cuts of beef have a different spectral view, as far as I understand. And then also looking for rot within fruit and nut, so like almonds. So really it's the camera that's changing in that type of application. In And as long as it's, let's say it's a Gigi Vision camera or a Gigi Vision compliant camera, then, the system doesn't change all that much. You're just swapping out the camera for hyperspectral. You're still doing AI processing. Your processing is going to be a bit different because instead of, basing your decision on images with hyperspectral, you're basing it on frequencies, but very similar. You mentioned where we get into some medical applications is not so much on the product itself, but more of the pieces around the product. So like glass vials, we've got a couple of projects that were in early stages of discussion, but they want to use they have an already installed machine vision application for doing glass vial inspection, but they're getting a lot of false positive off of those products because of the glare off of glass. There's a certain amount of tolerance for what's good and bad for the vial as well, like it's looking at the top edge. So they're keeping that traditional machine vision application, but they're adding AI in an embedded application running in between the camera and processing. So I don't know if that.
And how would it might change? Is there anything different in dairy? We do some dairy up in this region as well. Yogurts, milk,
Yeah.
creams. Is there anything other than say the environmental considerations that you have to, be aware of that would change for in a multispectral or something like that? What'd you call it? Hyperspectral?
Hyperspectral, yeah. Anything that would change. I mean, the main thing that would change is actually probably your lighting. It's the mechanicals around some of that system. For dairy, like, are you actually looking at the product itself under some sort of multispectral camera?
Well, and I don't know. I was asking almost more from the perspective from yogurt, but we also do a lot of different kind of soft cheeses in the area. And some of it is grown as a soft cheese and some of it's processed as a soft cheese. Or, like a, I don't know, Velveeta, right? Something that would become a Velveeta cheese. And yeah, and it's not necessarily cheese. It's more chemistry, but it might also, some multispectral is what I was wondering. So thank you. Good, good feedback.
I mean, the benefit with that type of application, you can basically see inside the product, right? And it's, they're the best use case around, I call it hyperspectral, but it's probably apples, right? And being able to see bruises that are not discernible to the human eye, but in the product, so that they don't end up at the store shelf with a bruise that then appears a couple of weeks later. I imagine it would be sort of similar in dairy, right? Where you're looking at some sort of there's some sort of frequency around or like
contrast of some sort somewhere.
Yeah, like a spectral difference between what is good and what is bad or about to go bad. But
super. Thank you very much, Ed.
Yeah. Yell out any questions as we go along. So really, when it comes to integrating, whether it's an embedded product or an embedded board into these types of vision applications, very similar to what I just showed, right? I'll start on the left this time. Like I said, all of a sudden these types of products are widely available and readily available for someone to build their own vision system. So on the left side, it's important that you provide these users with some sort of low code to no code type of software development platform so that they can design their own applications and deploy them onto the board. Like I said before, one of the things that's often overlooked is, I can develop a camera system on an embedded board, but I need to be able to integrate that with, different parts of the factory, whether that's mechanical systems or software systems or between devices, right? And that's where we're seeing a role for our expertise around Gigi Vision connectivity in these types of applications, right? Providing a software-based connectivity solution for embedded devices. And then again, the same
Got
as,
another question.
yep.
Kind of feeding off of what Tom was saying, do you ever work with drones, putting, like, smart devices on them? Because I know, like, several years back when we had the 35W disaster, there was a lot of focus on how to check the stress fatigue on various bridges in the state. And it's one person can't really do that, but it's sped up a lot. If you have drones that can make it a lot easier to get in certain areas. And I would just with the low power devices you've been talking about, I could see them easily fitting on the drone and the power requirements.
Yep. Yeah, for sure. So we get designed into drones around those types of applications. Traditionally, where we've been designed into those applications has been around the connectivity between an image source and a processing that's running on the drone. And then these drones have been used in agriculture, where you're going over these vast farm fields and you want to be able to inspect your product without sending people out there to do it or doing by aircraft. Infrastructure types of inspection is a big one. So sort of like what you're talking about with, it sounded like a bridge, like a lot of utility plants are now starting to use drones to go and do inspection of the facility. Roadways, we had a couple of applications in Asia where they were using, it was more of like a vehicle-based drone type thing to do inspection around tunnels going under waterways, looking for damage and signs of leaks and all those sorts of things. Probably, our area of expertise there has more traditionally to date been connecting the camera to processing within that drone. I suspect over the next couple of years, we're going to see a much wider push around developing smarter applications in those drones as well, right? We're giving people the tools so that they can develop an AI application in that drone. I mean, actually jumping back to the last question, like the idea of hyperspectral imaging right now, that's still a very expensive camera, but as those camera prices drop, I wouldn't be surprised to see hyperspectral imaging with, some sort of AI running behind it to help make decisions running over agriculture fields. Because again, a lot of sensor technologies that I've seen in that space, you're putting something out in a field to look for, soil level, dryness, wetness, soil conditions, all of that sort of stuff. I suspect over time that becomes drone-based technology. So overall, for us as a company, the move to embedded, it's definitely forcing some changes, some good, some bad. One is definitely price pressure. Jason, sales guy for Minnesota, he definitely feels the price pressure. For us, we've gone from basically 22 years of supplying primarily hardware into these types of applications to now a real push towards software and lower cost. And meeting the same performance requirements, but in software instead of hardware. The pace of technology is really fast. So, that's new processing options, new operating systems, new tools available. I just pulled out the example. So the platform actually that Dwayne's going to show in a couple of minutes, over the lifetime of that product development, which is only a few years, I think we've seen NVIDIA put out 3 platforms that would be very specific for our application. I think we're 2 generations behind, I will say, on where NVIDIA actually are. And that's over 3-4 years, right? So for us coming from a primarily hardware background, it's a rapid pace of change to try to keep up with. There's a bigger focus on the end user, which is again something different for us. We would be primarily providing components into systems. We didn't have a lot of interaction with the end user. Now all of a sudden, even when it comes to our SDK that we provide to to manage and control these devices. There's a user element, a user interface now developed into that SDK that makes it easier to use. And there's tools around developing applications in that SDK intended primarily for an end user so that they can design their own applications. There's a lot of challenges too for us around, or any supplier in the space around integration, right? So like I said, you can develop these products quite easily when it comes to embedded, but it's a bigger challenge to make sure that they can support real-time and latency demands in a industrial automation application. For us, it comes up more and more around data security and data management, which is, again, for us, an area that we'd never really dealt with. But as we get into AI in the manufacturing space, all of a sudden we're dealing with data going through our network that maybe in the past we had not dealt with. And there's a lot more emphasis on making sure data is locked down and not being shared. And then just when it comes to factory floor integration. So a few years ago, we really only had to worry about machine vision standards. It was Gigi vision and USB 3 vision for us, and that was all we had to know. And now all of a sudden we have to also be aware of all the other standards going around OPC UA, MQTT, what's going on in the EtherCAT world, because this is all coming together and starting to play a role in our products. So that is the machine vision side of what I was going to talk about. Now, this will feel like a huge shift of gears here, but it all sort of fits together in the end. There's a lot of new markets really for vision. Medical, agriculture, which came up, infrastructure, which actually came up in previous questions, and then different types of inspection. For tonight, I just chose military as a market to take a look at, mostly because for us, again, it was a little bit of a change in that we had to think way more about the end user. And then also it's a fast pace of change in that market, but maybe a little bit slower than what's happening in some other markets. And also it's just cool to talk about. It's the only thing I could ever explain to my kids that made them excited. If I could show them a tank and say our products are in that tank, they thought that was pretty cool. Now they're older, they don't care at all. So there are a lot of parallels between military and machine vision. One is, lots of installed infrastructure, lots of legacy interfaces, equipment that's difficult to replace because it's reliable and understood by the end user. But if you look inside most modern vehicles, and this isn't an entirely modern vehicle that this image is from, it's a mess of equipment in there. And I could never understand any time that we got the chance to go into some of these older vehicles that are still in use, just the array of information that was in front of a driver or a crew commander. And a lot of the time, it's just technology being added on top of technology, and there's no interface between it. And they're constantly switching from device to device to try to get the same amount of information, but from different imaging sources. Very inefficient. What most are working towards now are, more of a network system, sort of a top-down approach, building off of techniques from machine vision around Ethernet networking so that you can start to connect sensors to single points of display. One other thing, I think I touched on it later on a screen, but it's sort of interesting and you can see it in this right side image. This driver, he still has a window in front of him, so he's driving by sight. But a lot of the newer vehicles, they take the windows out as well. And then the driver is driving by camera and sensor because the glass is one of the biggest points of failure inside the vehicle. So if they can remove the glass, then it's safe and secure, but you need real-time connectivity between those cameras and sensors back to the driver with almost zero latency so that they can not get stuck down a dead-end road. For us, we got into the military business really with commercial off-the-shelf products that were being used primarily in prototype types of designs. And then once they were going into production, usually they would go to something more ruggedized than what we were offering. Then over the last couple of years, we started getting further into the market and now have our own ruggedized solution that's basically an Ethernet network switch that goes inside a military vehicle. It's going in a turret right now, and then has some wider applications as well. The thing that really changed for us when we were developing this product was understanding the end user. So again, it's a little bit like what I talked about in vision, how now all of a sudden we have to be aware of the end user. In the military space, we had to really be aware of who is the end user for this product and recognizing they were operating in a little bit of a different environment than what we usually be in terms of, very high pressure. And they really had to trust that system. And if they didn't trust the system that we were helping provide, they would turn it off and start looking at other ways to navigate the vehicle. And unfortunately, in a lot of these vehicles, that means sticking your head outside the vehicle, which is not what you want to be doing. They want to stay inside the vehicle as much as they can. The concept itself had been around for a number of years, this idea of video-based situational awareness. But 15 years ago, on the machine vision side, we weren't really keeping pace, or we hadn't quite reached the state that they needed to be at in terms of almost zero latency from camera to processing. And there were still a lot of network challenges around easily transferring images. I'd say over the last 10 years, a lot of that changed. In the machine vision space, I think we solved a lot of that networking, latency, and sensor management issues. Even in our traditional machine vision types of applications, we're often managing multiple cameras and sensors to different types of processing. And now more and more cameras and sensors to edge processing and different points of processing in an application. There's also been a change in the military market itself in that they're more interested in looking at some of the standards that are being developed in other industries. So the GIGI vision standard is a backbone in a lot of the video transport standards that have been developed for military applications. And then just a willingness to look at commercial off-the-shelf products just because it's faster than internal development projects. Like I said, oftentimes those commercial products then become a ruggedized product as they move into actual production, but much more willingness to go and take technology from other industries now in the military space. So this is basically what a local situational awareness application looks like, and what we're helping do. So in this type of application, like I said, they've removed the windshield and the camera. The driver up at the front left, I say he or she is navigating by camera and sensor around the vehicle. All the information that the driver gets is also available for a crew commander. The crew commander can then decide what information that he or she wants to share with the rest of the crew, who are usually at the back of that vehicle. We've been told that depending on the situation, sometimes the crew commander doesn't share all that information with the people at the back because they don't necessarily want to be knowing what they're stepping into if they have to leave the vehicle. It's sometimes better to, I guess, switch to human sense at that point. A big value of going to this more Ethernet-based networked approach to your cameras and sensors in these types of vehicles is that you reduce the weight. You take out a lot of cabling. You're able to move to smaller processing technologies. So instead of large processing in these vehicles, they can start to use single board computers, lower powered laptops, smart displays, and that sort of thing. And also just video and power over a single cable. I don't know if you've ever seen like the harness inside your car. Imagine that inside one of these tanks, right? It's that magnified by 100. So every bit of weight that you can remove from this vehicle makes it faster and more agile for being able to navigate. Basing these types of deployments now on Ethernet makes it easier to scale an application. So you can add new types of cameras and sensors. So even, spectral imaging type things, it's easier to add a GIGI vision-based spectral sensor to this type of application and start seeing data from it right away, rather than a proprietary system managing the single sensor. You have one software development platform managing the whole infrastructure from camera to display. So your operator our driver, crew commander isn't having to switch between different operating systems to see different sensor or camera feeds. It then also makes it easier, if a camera gets blown off one of these vehicles, you can fix it in field. It's basically a plug and play type of connection back to the Ethernet network. No different than if we lose our router at home, we can go get a new router and connect it back to our Ethernet network. Just the little bit of a different scale, I guess, when you're in a tank versus your Ethernet network. There's still a lot of work going on here that we're not so much necessarily directly involved with. We're providing more of the transport between cameras and sensors, but partnering up with a number of different companies that are looking at different ways to then apply AI in this space. With just some cool applications and really interesting stuff. So one is around driver awareness. So using cameras and sensors to warn of a possible rollover. I think I don't have the stat with me at hand anymore, but I know like most of the fatalities in these vehicles weren't actually from combat; they're from rollover, just because they're hard to drive. So this is being able to use a sensor-based technology to then alert the driver of, you're getting into a different gradient, or even, the road condition is changing from gravel to sand. So be aware. Threat detection. This is using things like object detection to alert the crew commander of threats that are out there, possibly that they might not be able to see, but you can train AI to start looking for anomalies out in that view, something that's a little bit different. It could be a tank, it could be camouflage out there that a sensor is picking up on, and you can alert the crew commander. I know in sort of our usability around that, the crew commander still wanted to make the choice, but he liked having it highlighted for him that it was out there in the field. And then hyperspectral or multispectral, which has come up a couple of times in the evening already, but hyperspectral, you can start to add hyperspectral camera sources or image sources to these devices, to these vehicles, and they can look for changes in the environment. So one of the big ones is a change in soil. Could, hyperspectral can identify overturned soil, which could mean that there's a mine on the road, or it can differentiate between camouflage and a natural environment to highlight that there might be something in the trees, that shouldn't be there. So that's where, what
One
types
sec,
of applications.
Barrett.
Yep.
One question.
In the threat detection side, and in both the ground-based vehicle as well as drones or flying vehicles, even subsurface marine vehicles, how much latency do you get in FLIR, forward-looking infrared, than normal vision or normal light environments? You get much more latency in forward-looking infrared?
To be honest, I don't have an answer for you there. I will, when it comes to these, the goal is almost zero latency, right? With almost all of these applications.
Right.
For us, and I should have said that our area of expertise here is really ground-based vehicles. We try to avoid things flying or in the ocean, because there's a whole other level of complexity to them. But yeah, no, it's a good question. And actually, if I can get an answer for you and pass it back to EJ to forward around.
Or Jason, whatever. Yeah, I get
Sure.
that.
What
Yeah.
would you be looking for in terms of latency?
Yeah.
Wasn't sure there was gonna be it. Yeah, because FLIR is just it's a different spectrum presentation.
Yeah.
So its speed is whatever I'm looking at outside of infrared, then I'm gonna be seeing that at the same, the lens is looking at infrared at the same speed that I would be looking outside. It's just a different perspective.
Well, certainly.
It'd be like asking, so what's the latency from normal vision versus
Infrared.
heat?
Yeah.
Heat would be this, it's the same. Because the camera vision, it'd be a different lens looking at that. I mean, you could probably overlay them at the same time. And then, I mean, still optically, they're looking at the same thing, but through a different, it's a different spectrum.
Yeah.
But the latency is the same. It's,
Yeah.
the eye's not transitioning, the lens is not transitioning to infrared. It's a different lens altogether.
But it wouldn't have to do any processing,
This
just
isn't-
like the data.
Well, because it's, because that's my point, is that, so if I have a camera that's looking at something, and then I have an infrared camera looking at something, they're both projecting, they're both then receiving the same information and presenting it at the same time. It's just a different perspective, but that's why, we don't have one lens on a cell phone. We have different lenses because they're doing different things at the same time. I'm not asking one lens to then switch from heat to infrared to, or thermal to infrared. I'm having a different lens do it differently, because it would be like what would be clear on a normal lens? You'd be asking it to do a software interpretation. There'd be latency because you'd be asking for an infrared interpretation of actual, of standard vision.
Yeah. And
Yeah.
that's the question, because I didn't know how much in these systems, is it software analysis that is,
The clear is different lens layer.
Yeah.
Yeah.
You had different lenses and different optics, right?
Yeah.
Or,
And to answer that question as well, a lot of our customers who are the camera manufacturers, they can handle the latency by their software by stitching the images at a certain speed based upon also the processor that's in the camera itself. When we look at thresholds, like in military applications, especially for situational awareness or in cases where an armored vehicle or brigade vehicle is being driven visionless by a driver who has no physical sight lines to the battlefield that they're driving in. The military has deemed, this is the U.S. military, that anything under, typically scientifically, anything over 50 milliseconds of latency theoretically causes motion sickness to the typical person. And because of that, the latency has to be much quicker. Otherwise, a driver wouldn't be, their brain wouldn't be able to process the images quick enough for them to feel like they're having an impact, say, on the steering of the vehicle. I do have some applications and some customers who are manufacturing cameras, high speed, very high resolution, plus 30 megapixel cameras that are actually getting, for drone applications, are actually getting strapped on the belly of a Cessna and being flown over a certain topography to do mapping. And these are aircraft that are, traveling, 200 plus miles an hour, and they're using our embedded high-speed DECA interface to use their software to stitch these images together at incredible speeds so that they can get a very large field of image very quickly due to the speed of the actual vehicle. And that's the same thing with manned and unmanned drone vehicles as well. The speed also has a lot to do with it. And again, that's not also being handled by the camera manufacturer software, our EVI, our embedded Ethernet vision interface, along with the manufacturer's software, who's doing the end-to-end processing back to their box for processing and storage of images.
So what's more difficult? Mapping the Earth at 200 miles an hour from a Cessna, or catching the deviation in manufacturing of one unit at 200 units a minute? They're almost
Yeah.
equal. If you think about the economies of scale, the speed at which you're processing is, it's extraordinary in both cases.
Yes.
Yeah. Yeah.
And
No,
these images in that drone application have to be stored on a drive as they're being captured.
Right.
Yeah, it is pretty amazing at the speed automated decisions can be made. Absolutely. So yeah, so when it comes to the military side, I mean, lots of parallels with what we've seen in machine vision in terms of, a move towards standards-based connectivity, uh, definitely a move towards embedded computing, looking at different ways of sort of reducing that central processor down to multiple processing running around on different points in the vehicle. And then for us, a real focus on the end user. So we went from providing components to really having to understand how does the user interface with this technology, which then takes us to the last portion of the presentation. Dwayne will get to talk shortly. Um, in the last couple of years, we took some of the trends that were happening in terms of AI. If I go back a few years ago, we had customers in medical imaging talking to us. This is probably 5, 6, 7 years ago about the idea of AI, and could they start to do AI-based processing on that image as it was, as we were capturing it and transferring it. Was there something that we could help them do in terms of AI, in terms of helping that physician then at the end identify anomalies or spot differences? Medical market moves pretty slow. I don't know how much more work we've done a little bit of preliminary work with a couple of customers and a couple of more on the research side in universities. But the idea sort of gave us a bit of a germ of an idea of what else can we offer as a traditional connectivity business, and how can we expand the business? And that brought us into more directly onto the manufacturing floor. So like a lot of us, when we think of manufacturing, we think of something that looks like this, right? It's a robot moving pieces around. As one of the previous commentators just said, it's parts moving at a tremendous speed under a camera for automated processing. That's certainly true for a lot of manufacturers, but the reality is when you go onto a manufacturing floor in North America, this was a stat I pulled out from a show a couple of years ago. About 70% of manufacturing processes in North America still rely on a human decision. That could be a quality decision. It might be physically manipulating and moving the part, in this case, filling the product, moving it, labeling it, putting the cap on it. There's tools doing it, but there's also humans involved in the process. It's especially true if you're manufacturing sort of a higher value, lower volume mix with short production runs and customization for end clients. It can be really expensive to implement full-scale automation. So a lot of manufacturers sort of sit at this, what I'll say, level 1 stage. They rely a lot on human labor and human decisions. If they have started to automate processes, they're usually sort of in this level 2. They've got data sitting in different information silos. Sales and inventory processes may be digitized and automated, but manufacturing directions still rely on a piece of paper traveling around a shop floor. Most of the people that we deal with, they aspire to at least a level 3. They want to get connected tools, technology that supports, or in some cases fully replaces, the human process and the decision, and then data around those processes is shared across the organization. But the path to get to that level 3 can be confusing, time consuming, and on the surface, it can also be expensive. When we start working with a lot of manufacturers over the last couple of years, this is sort of what their journey looked like. They usually have a problem that they think can be solved by technology. Media and marketing have done a really good job at hyping AI. In my job title as product marketing, I sometimes take a little bit of blame for some of that hype. Manufacturers build a lot of expectations around a perfect use case, and quickly they start to run into issues. The application is maybe not quite as straightforward as what that perfect use case presented. There's a lot of customization that could be required. A common issue is just simply acquiring the images required to build and train an AI model. it's a question maybe to say for Dwayne when he's doing his demo, but you need a couple of hundred images of a product to build a properly running AI model. This is especially hard if you're manufacturing unique or lower volume products. And then if you're starting with a very manual process, there can be a bit of a sticker shock, right? Like smaller operations, they don't usually have the time or resources dedicated to manage these projects. They also have a business to run. And then maybe one of the bigger ones, and one that often gets forgot, is the human in the process. So even with automation, many processes still require a human decision at some point. And you can't forget the human as you go to automate that process. That can be as simple as explaining to an operator why do you want to automate a process and providing the training so that they can apply their expertise in new ways. So one application we've been, by coincidence, over the last couple of days, talking to a couple of different customers about is around robotic welding. And their goal is to remove the human from that repetitive, dirty, dangerous work. But they still want that expert there watching the robot, looking at the weld afterwards, at least for the foreseeable future, because they have an expertise that is hard to mimic with technology. But if you don't communicate and train your employees on why are you bringing in automation, humans are pretty quick to dismiss technology and resist change. That's just our human nature. So then what happens is the manufacturer ends up back at the status quo. You haven't really gotten anywhere. There's a lot of large manufacturers stuck at this slope. We did some early work with a large manufacturer who are now, I'm going to say, about 4 to 5 years into an AI project that still has not deployed past an R&D lab. We usually come into the process with most of our manufacturing partners around this bottom downward slope. If they're at the bottom, that usually means they deployed a solution and have been disappointed with the results, or they've hit a roadblock or pain point along the way. Ideally, we can meet them before they begin the downward journey. And in some cases, it's yes, we can move ahead towards an AI solution, especially if they're already using machine vision in their process. More often, what we end up doing is taking a step back and understanding that AI and automation is the end goal, but are there ways that we can get there in a more phased approach so that you can also overcome some of the concerns related to cost, complexity, and employee buy-in? So that's usually, solving your first problematic process, maybe giving a human decision support tools versus trying to quickly replace the human in that process, digitizing work instructions, adding a visual inspection element to that so that they're always making the right decision, but still keeping the human moving the part, right? Moving the part is sometimes more complex than the AI side of these applications, to be honest. And then for a manufacturer, you can get some quicker ROI and data that then helps you guide your strategy. So just in general, why do we need these types of decision support tools for human processes? I always just use this slide and say, try and count the white dots, now count the black dots. Over an 8-hour shift, I'm going to ask you to switch. You start to get pretty bored. Your eyes start to play tricks on you. There's about a 20 to 30% error rate in most manual inspection tasks. And actually, a high percentage of that error rate is where we're just, we're not trusting our own decision. And actually the product is fine, but we start to doubt it. So we did work, one of the early evaluation customers for our product was a distillery. And the quality manager there, his main pain point was he would look out on the shop floor and he'd have 20 employees all gathered around bottles looking at labeling that was done half automated, half by human. And, operators arguing over whether it was off or on. And it would usually just be a matter of a few millimeters of difference, but all of production would stop as people started doubting the labeling. And then I will turn it over to Dwayne here.
All right, thanks, Ed. So yeah, as Ed has mentioned throughout his presentation here, we've been venturing more towards into the manufacturing solution space with our platform called Vera. So with our Vera platform, it's a complete turnkey solution where we're helping to provide basically what you see here is kind of what you're going to get. So this is our tabletop inspection unit. So we're providing the camera, we're providing the hardware, we're providing the lighting, the software, the application, the edge device, the AI component, all within this one system here. So I can explain a little bit on the left-hand side here what's actually happening on our inspection unit here. This is one of our earlier units. It's now a little bit cleaner, a little nicer, a little bit more marketing onto it as well. But in the top portion here, this is where your machine vision camera is going to sit. We protect it from the enclosure and within the enclosure just for any sort of environmental elements. So with our system, we're camera agnostic. So depending upon what the customer is going to be inspecting, depending on what the working distance is going to be, just depending upon what lighting is available within the facility, or a lot of different environmental factors, we select then the best camera, the best lens that's going to complete that job for them. Now that machine vision camera is going down into this shrouding. So this shrouding is doing a couple things, and a couple very important things. First and foremost, it's protecting from the environmental lighting, so any sort of ambient lights coming in within the factory. So when you start talking about AI and vision, one area that gets overlooked, but it's probably the most crucial component of the entire thing, is proper lighting. Proper lighting can affect your model. It can affect the results of your model. It can start to affect the results of your machine vision outputs. So we try and do our best to kind of really create that pristine environment. So on the inside, on the shrouding here too, we also provide our own lighting. So we have our own LED lights that are pointing up to create a couple points of reflection before coming down onto that base plate. Again, what we're trying to do there is create what we call that cloudy day effect. So trying to eliminate any sort of shadowing, eliminating bright spots. We're not getting as much reflection. If there's something that's really shiny down on that board, it's not going to be, again, those lighting elements can affect your model and start to affect the results that you're seeing. And then within the Vera platform itself, we provide a number of different types of templates for visual inspection, for digital checklists, digital work instructions, different traceability applications. We also have our built-in AI model building tools. And then again, yeah, you can't these days with Industry 4.0. You need to be able to communicate with the entire environment. It's not just being siloed and holding on to that data that you're capturing from the line. You got to be able to share that with the machine, the machines themselves. You got to be able to share that with other software within the environment as well. So we've got connectivity directly to the PLCs going either, like I said, OPC UA, MQTT. We can go direct Ethernet IP, just going directly down to controlling the machines. We've got REST APIs. We can connect to the different MES systems, ERP systems. We can do database connectivity, push to the cloud. You need to have a Swiss Army knife of being able to push those data.
All right.
Next one.
Do you want me to? I can stop sharing and you can share your screen.
Yep, sounds good. So what I'll do, just I know we're starting to run out of time here as well. I'm going to go through one of our applications, and then I'll show you a little bit of our AI model tools, and then I've got a few videos and some different use cases that we've done for different customers that are I think are interesting, that we can take a look at some of those as well. So what you see on the screen here now, so I've already entered into one of our applications. This application is our visual inspection application. So this would be one of the templates that we provide. This one provides a bit of a combination between traditional machine vision and in adding in those AI elements into those AI components. So when you're coming in, this is one's more sort of designed for like an offline manual inspection where somebody's having to actually take a part or take whatever they're going to be doing their inspecting, taking that to an offline station and doing their physical inspection. So in this case here, I've got this kind of demo geared more towards electronics and PCB manufacturers, but this could be transitioned to kind of really any vertical. So when you're first coming in, just a little bit of metadata about the inspection that's being done. In this case here, I'm just looking for the username of who's going to be completing this, and then any sort of serial number. A serial number could be read from a barcode. We could do OCR. We could scan it in. You could hand bomb it. We can add fields, subtract fields, change fields. Our product's fairly diverse that way. We can easily add things and kind of move things around here. So I'm just going to hand bomb something in there real quick. Now I'm switching down in the comparison section. So in this application here, this is kind of where the more traditional machine vision is taking place here. So what we're doing is we're taking a golden reference. So this, in this case here, this is my golden board. This is what every board needs to look like. What we've done here is again, just for demonstration purposes, we've added in some defects, but the typical kind of flow of this application would then, once you've got your reference, your golden image, then to place the board in the shadowing here, it doesn't need to be perfectly lined up. The software is going to auto align if anything's misplaced. And then what it's doing is it's doing a pixel by pixel comparison. And then it's going to start to highlight all the differences that it's found. So once I hit that comparison button, now it's doing its analysis, and now it's starting to highlight all those areas which it found differences from my golden reference. So now we've moved down to the review section here. So the review section, what it's doing is it's so highlighting those different areas that it's found differences, and it's showing me the reference versus the sample. And in this case here, we're just giving the operator the opportunity to say yes or no, whether or not this is or is not a defect. They can add in any sort of comments here as well. And this is going to start building out a report. But also what you're doing here is when you're saying yes or no, this is or is not a defect, you're starting to build out an AI model. So we're taking your decision, we're going to start adding that into a model. So if I come down to this section real quick here, I have this AI assistant. Right now, this is the model that I've created. And right now I'm saying save images for training. So basically, as I'm making my decisions, it's going to be saving those so that later I can train that model. And then I can turn that model on for future decision-making purposes. Or I can turn it off, or I can turn it on. When I turn it on, it's going to start telling me that based on everything that's within the model, AI determines that this is an accept or a reject. And we can start kind of assisting the operators in that manner. But back to this one here, I'm just going to add in a couple of comments. We can see that that is clearly broken. And I'll say that, yes, that one's a defect. And it's going to start flipping through all the differences that it's found. I won't go through each one of them. But we can see here we've got flipped polarity. There we go. I'll say yes, that one's a defect as well. This one just has a missing label. So again, I'll add in one more comment here as well. Missing label. And I'll say no, that one's not a defect. I'll just kind of skim through the rest of these ones because you guys probably get the idea. So now that I've gone through each one of these, I can come down into my reporting section. So now what we've added here is the ability. So if this was a good board, you would just hit pass. You can go on with your next inspection. If it was a failure, you can assign a reason code to that failure. So if you want to start tracking a little bit of analytics on reason codes as to why things are being scrapped or why things are failing, we're going to capture that information as well. So I'm just going to say that this one is damaged, and I'm going to generate report. So what that's basically doing now is building me out a PDF report based on the different stages that we've gone through here on the application previously. Some of these other buttons I like to just point just so we can share a little bit of different functionality here. So if you wanted to just upload this to SharePoint, so if you were like in aerospace, for example, they need to capture all of this inspection information and they have to store it for 50 plus years. So being able to store that digitally as opposed to having that printout of some sort of paper-based inspection, it's going to be a much bigger time saver than having to print all that out. Or let's say, for example, that this was going back for rework. So we've noticed that it's got some defects that can be fixed through rework. We could just automatically send this PDF to whoever can be doing that rework. Show you what that PDF looks like. So as we're going through here, it gives me my status. So that's what I entered as my root cause as to why I failed this. There's that serial number I entered, that username. This was the sample that we placed underneath the camera, and it's just highlighting all the different areas in which it found differences. And then it's going through that same review section, and then we can see what the status that I entered and any sort of comments that I entered there as well. So again, if this was going to go back for rework, you'll have the board, you'll have a detailed report, and you can see very quickly exactly what areas there are the problems and what needs to be fixed. Or if this was going to be scrapped, again, for like aerospace or whatever regulatory purposes require this information, you've got a very detailed report as to why we scrapped serial number XYZ. So now coming back into here as well. So as I mentioned, as you're entering in your different reason codes down in the bottom section here, this is I've got some older data in here as well. We can start building out some different analytics and just being able to plot point those different failure reasons. You can just create some pretty simple Pareto charts. So just being able to take a time frame and kind of dig into see what my biggest hitters are here. So in my case here, I can see that I'm having assembly issues, which seem to be kind of the biggest reasons that I'm scrapping things. So I might want to dig into that process a little bit. Is it a training issue? Is it certain operators, or is that they're not having proper equipment? So now let's maybe plan like a Kaizen event or something along those lines to see if we can kind of figure out what the issue is there, and then we've got the ability to come back after a few months, see if the changes that we made are actually making improvements, and we're seeing some of those numbers go down. So that's our main visual inspection type application. What I'll walk through next is we can take a look at more of some of our AI tools. So as I close out of this application, what you're seeing here, so this is our main platform. So our main Vera platform. Each one of these different tiles is a different application that I've created. And then also in the top portion here, you can see we've got this AI section. So when I go into the AI section, this is where you can start utilizing our built-in tools to start building out different types of models. So I referenced this boards one as I was going through that previous application here. So if I dig into that guy here, I can see my accepted and my rejects. So as I was accepting and rejecting things, it was adding to my model, which can be then trained and utilized later. So we can do classification models and we can do object detection models. I'll walk you through a use case on each one of those, just for a different customer project we're currently working on. So I'm going to jump into the seals one. So we're working with a customer right now where they make these rubber seals for gaskets and for different types of lots of different types of pistons and a number of different types of applications that they have. The problem that they have is they have 13,000 different SKUs. So if a seal gets returned or if they need to send out a new seal to another customer, it takes them a very long time to determine what seal it is, especially for any sort of new employees. So just a proof of concept for what we've done here is they sent us a few different ones that are actually fairly similar in view, but they do have some differences, slightly different contrasts that we were able to then build a classification model so that all they have to do is they place the seal underneath the camera and it'll immediately tell them what family that's a part of. And then what they were also requiring was a little bit of measurement so we could completely tell them exactly what they were getting here. Let me just run through that video so you can see what that actually looks like here. So that's then placing that seal underneath the camera. We would click the identify button. It immediately can tell us what the family is. When we click the measurement button, so they're looking for the OD, the ID, and they'll need the height. So we actually added in a 3D sensor in there. So it's able to pull off those different measurements. So now they've got the family of seals that they're looking for. They've got the OD, the ID, and the height. It's a whole lot easier for them now to figure out which seal the customer is going to be requiring to send back to them. So before that took them a lot longer than what this is taking them. So granted, this is a very huge model that they're building out here because they have a number of different types of SKUs, but yeah, the time saving here is kind of what's the big selling point for these guys. So next, I'm going to go back into the AI model here, and we'll look at an object detection model. So I've got a few different object detection models that we can take a look at. Let's go into this guy. Actually, oops. Let's just reload that. I don't know why that's doing that. There we go.
Just roll Microsoft.
Where's the one I'm looking? Oh. So in this case here, so this is So this is a company that we're working with that does makes metal plates that go into aerospace. So the issue that they were having is they need to be able to determine a hole that is countersinked versus just a straight bored hole. And they also have to validate that it's in the correct positioning. So they've sent it to customers before where they didn't have a countersink, where there should have been a countersink, and that causes a lot of problems when you're trying to attach that to, say, like a spaceship or an airplane. That just gets sent back. So what we've done here, if I say delete one of these from now, so within an object detection model, you can come into the object detection model, you take your pictures, you create different classes. In this case, we called them the shiny hole versus the dark hole. So in this case here, I've just have my shiny class selected. So then I'm just starting to teach the model what a shiny hole is versus what a dark hole is. So in this case here is just about annotating the images and just teaching the model that way what the differences are, what the different classes are. And then we provide all of the tools within our UI. Then you can configure your training, you can train your model, then you can select your model to start using that model there as well. So I'll show you what that end result there looks like. I go back into the application here. So again, here, what these guys were doing is first they have a good board. So they're using a little bit of the similar application that we talked about. So they have a good board so that they know basically where all of the countersink holes and where all the straight board holes are supposed to be. So basically what we're doing in that case is we're detecting what type of hole it is. We're remembering the coordinates of all the holes. And then when they're doing their different samples or their different inspections on the next board, we're able to quickly tell them, yes, this is good, or no, you've got the wrong type of hole in this location. So as I put one down here, again, you don't have to be perfectly aligned. That one's just doing a quick inspection here, and it's collecting all the information. So that guy's good. It got them all in the correct place. Now I can go to I'll show you a failure test case. So this would be a bad one. So we can see down in the bottom left here, we can see that this one has a countersink where it shouldn't be countersinked. So when you're looking at that based on against the, so we can see, well, there's actually another one on the right-hand side here too. So basically then in this case here, we're highlighting the ones that were wrong based on it's the wrong type of hole in that coordinate. So we've been able to then, they know that just scrap that board. They're not going to be able to send that out to a customer because it's already been a board hole that are countersinked hole where it's not supposed to be countersinked. So that's just a couple different use cases. I know we talked a little bit about some food. We talked a little bit about some other areas. I've got just a couple more videos. I can show you a couple different use cases and some other, it's just some other verticals in which AI is being used.
Hey, Dwayne, can I ask you a question real quick?
Sure.
This is so in my experience, one of the areas that I've seen where that continues to be kind of lacking, and I'm wondering if you guys have a solution to this, is the case of especially when it comes to like robot guidance, bin picking, things like that, overlapped or stacked parts, if you know what I'm saying. If I give a human a bin full of parts, right, and they know that there's 600 parts in this bin, but they're in a big pile in there. Even a 5-year-old kid could pick one part out with their hands, and put it onto something. So if I had a robot tending a CNC machine or something like that, a 6-year-old kid could take that part out of the bin and set it in the machine. But it seems to me that we still struggle in machine vision to actually set up machine vision systems that are able to look at a cluster of parts without the aid of a vibratory table or some sort of fixture where we physically human manipulate them to put spaces in between them so that the vision system can detect an individual part. Have you guys done anything with that, or have you seen anything with that?
So that's where AI is going to come into play too. So you can start training some different models for having those different stacks, those different piles. I've actually got a little video I can show you on that as well. It won't be to the degree that you're, wrong one. So this was just a demo that we run at a trade show where we've got a little conveyor belt. We've got nuts and bolts. We can kind of move them around, sort them. Basically, what it's doing here, we've trained the AI model and taught it what a nut is versus what a bolt is, and we've told it just count how many nuts you see on screen at one time. But I can go in here, I can start piling things together and moving them around, and it's going to immediately pick those up in real time, and it's going to highlight those for me. So it's all about how you train that model. So if I've trained it to just be separated, it's not going to pick it up when they're stacked. But if I've trained it when they're separated, when they're stacked, when they're up, they're down, different orientations, it's going to learn what that looks like, and it's going to be able to adapt and still give you that result.
Very cool.
So just kind of going along those lines there as well. I'll go back to that one that I almost started there. So this is just a different type of AI model here. So again, we're just looking at a PCB board. We found out in this case what a missing screw looks like. This is just kind of show you that as soon as things come into view, it's going to start to kind of analyze it. It can be in any sort of orientation, but once that's in front of the camera, it's going to be running that model. It's going to be able to pick that up. So as soon as I put that in the view, it knows I had missing screws there. One other kind of a couple of other cool ones that I like to walk through. It kind of just more so to kind of get you some ideas. So this is a wire company we worked with where they have little strips of wire coming down. What they needed us to do is those little blips that you see. What they required us to do is as the wire's coming down, we needed to measure the stripped portion, the insulated portion, and the final stripped portion, validate that's within tolerance. If it's outside of tolerance, we need to communicate back to the PLC, stop the conveyor belt, so that they can go and they can recalibrate their machine. So again, this is a little bit of AI, a little bit of traditional machine vision, but just I like to show some of these just to spark different ideas. One more I will show. So again, when we're talking about food, we're working with a company that makes crackers. So we need to determine if the package of crackers is good and bad or bad, and we determine that by how much crumbs are in the package. If there's too much damage, there's just too many crumbs within the package, they determine that to be bad. So in this case here, you can see that one, there's a fair number of crumbs in there. So we had to teach it what a really crummy bag looks like versus a cleaner bag. So in this case here, that one we can see clearly that's a bad bag of crackers versus the other package that we had on there too. When we put that one back, it's going to immediately switch to a good. So we have in the top portion there, you can see it was class was none, and now it's gone. It's determined that's the good package. So that's kind of really what I wanted to show is just a little bit of our software and just kind of some different use cases and just yeah, some of the things that we've done with some of our customers to give some ideas.
It's awesome.
Yeah, that's good stuff. Very good stuff.
Got a question for you. At the beginning of your presentation, you were talking about how the AI computer vision has progressed using single board computers and microcontrollers that are like Raspberry Pi and that kind of thing that's accessible to mainstream audience. But one thing in that market that's been coming up the past few years is RISC-V processors, trying to get away from ARM processors and Intel processors. Do you know of any work done in that? Where it's
No,
more of
and
an open source chipset?
Yeah, I in most of our cases, those are probably the processors that we've been working with the most, I would say.
Okay. Interesting.
Your RISC-V?
Yeah.
Yeah. the RISC-V.
Sorry, I had more on the ARM side.
Oh.
Yeah, for us.
Well, I get it. I mean, that's that's available, and there's a lot of companies work with it. I mean, we definitely NVIDIA's worked in that, and
Yeah.
all right, definitely.
Yeah. Do you know what's the concern in that area? Do you know?
No, just trying to open things up so that
Yeah.
if you want to spend. I mean, the whole idea of open source is you don't
Yeah,
have someone else determines as a priority. You can customize things as you need to.
Yeah, I would get that, like just general observation. Yeah, for sure. I mean, you're sort of you've got a funny thing going on in this push towards open source, but then only a limited number of suppliers, right? Like especially Jason would have lived through a couple of painful years out of COVID, like just purely around supply chain, right? For us, where he just could not get parts and customers couldn't get parts. So I guess that would be probably the biggest risk looking ahead, right? Like how dominant can those players be and just being sole source providers? Like even NVIDIA is pretty unavoidable on the manufacturing side. don't know. We don't run into too much other than, you know, basically everyone sees our board and recognizes it's an NVIDIA board, and everyone says, yes, that's what we use as well.
Hey, Dwayne or Ed, you know, one of the things I know that you mentioned in the presentation is the importance of lighting. You know, and I've done some machine vision in the past, like dark field, bright field, backlit, all that crap that they do. But I also know the color of the lighting is key. And I don't know if in your Vera product, you guys, and you said it was LED, but do you have the ability to change the color of the LED lighting coming down depending on the part that you're looking at? Or
Yep,
is it all-
absolutely. We can. We can. Yep. So we build all that lighting in house too. So depending upon what is going to be required, we can change that lighting as well.
So, but it can't change, like you can't change it on the fly though.
Not on the fly. No.
No.
Okay.
We're
Like
looking
our
at a couple of
LEDs.
applications. Yeah. There's a few different, we haven't got past like the sort of early demo conversations with them, but a few electronics companies where they'd like to be able to change the lighting source to UV to be able to then look for conformal coating on the board, right? So they would have like their white light for doing the imaging, and then within the same unit, switch over to that UV light to also be able to look at the coating on the board. So it's things like that. We could have had our application engineer, and he would have been delighted to hear you ask about lighting, because that's his main passion, right? Like, and it is funny, and it's such an important part. Like, that's why we, you know, our original proof of concept around that Vera unit, it didn't have the domed lighting. And you were just so influenced by the environment, and the environment could include the operator, right? Who in the morning, it could be one person, and in the afternoon, a different person, and just the lighting changes. I always say the biggest challenge is lighting, and when things don't go right, it's usually the lighting people's fault. So
I teach a vision course here in our lab. We don't have any shrouding or anything. And I would come up to like a student, they'd say, hey, I got my project ready to sign off. And I'd come up over to watch them sign it in a white shirt or something. And all of a sudden it wouldn't work when I got there. I'm like, well, what's going on? It's not working. And then I'd walk away, and 5 minutes later, I don't know. Every time you walk up to it, it doesn't work, you know? So a shadow or the brightness or the reflection or whatever it is could change it on the fly.
Anytime we go on site and we have our application engineer with us, like as soon as he walks in the building, his first thing is looking, are there windows in this building? Like that's what he's always like, or even will lighting change, right? Like if you're doing in some of these electronics applications, there might be like some welding nearby, right? And he's like, is there any welding going on here? He's always looking for that stuff.
The flicker and flash can really kill you. And in an earlier career life of mine, I worked for a packaging equipment company, and I remember when you said your application engineer, we had a guy who would not do any of the machine vision as part of the factory acceptance test. He said, we got to do that as a SAT test at your site, and we'll set it up there, because things will change between our floor and your factory. And the people, you know, it usually took a couple conversations to confirm, for them to get an idea, and then they'd agree, and then it was okay. But it was usually a little bit of a struggle initially. Why can't you put that in our factory acceptance test? And it was always a negotiation point.
Yeah, I mean, even with the shrouded lighting on that unit that Dwayne showed, like it does a pretty good job, but you still have some environmental influences, right? We'll usually build like a sort of prototype eval type of model on site to show a customer, but then say, you know, really when it comes to model development, we should be doing it at your site, because even if you send us products and we build it, it's going to change a little bit when we get to your site.
Oh, in Texas, where they wear those big cowboy belts, and you're getting all the reflection off a tabletop.
Yeah.
Teasing, of course, but great presentation, gentlemen.
Yeah, thank you guys so much. I'll give you guys
Okay,
a
good. Yeah, it was a little longer than I'd expected. I just sort of put together a couple of different sets of slides, but it was sort of, you know, the idea of trends, and it's interesting because they feel like really disparate end markets and end businesses. But for us, there's so much commonality, right? Like it's you know, the embedded things that are happening in machine vision, we're seeing in our own product for manufacturing, and the focus on the end user that was so important. And as we've gotten into military applications, that sort of translates as we start doing AI for manufacturing, and you're really looking at, you know, that example that Dwayne showed of the metal plate, where they're looking for countersinks. Like they do a lot of low run of that product, and they really want their quality manager to be able to train that application himself. So you have to make sure that it's a really simple tool to be able to develop an algorithm and deploy it.
Well, I'd say nicely done. Very nice tools and very good examples, and we appreciate it again very much.
Yeah.
I just don't want Jason to get you guys to come in. He and I have been talking about this for 6 months or 8 months. So thanks again.
Thank you guys so much.
Great. Thanks, guys.
Yeah. Thanks a lot, guys. If you have any questions, you can follow through Jason, and yeah, thanks for your evening.
Thank you, folks.
Thanks,
All
everyone.
right. Thank you.